All right, good morning and welcome to our third class and what will hopefully be our last digital session for the semester. Knock on wood. But the plan is to return to the classroom starting Monday. So, yeah, so it'll be an earlier wake time for all of us. Because class starts at 8:15, and yeah, I was telling my wife this morning, I'm like, this is the last morning where I get to say, okay, bye, I'm walking upstairs to work. Like, I'll actually have to drive, which is going to be, a whole other thing. But anyways, um, excuse me. So we left off with talking about density, and there we go. And I left you with one doozy of a practice problem. Density, the equation for density is it is a ratio of the mass of a substance or an object to its volume. And we left off with the following example. So we have 0.402 grams of a metal occupies 0.908 milliliters of space. And then there are two parts of this problem. Part A, determine the density of the metal Part B, determine the volume in liters that 58 kilograms of this metal would occupy. All right. I guess before we go any further, I should highlight my Nicolas Cage mug. It's one of the ones that as it gets colder, it turns black, and then my sister gave it to me, and it is the best mug I own. So that way it won't be distracting as I take sips. You're like, wait, what's on his mug? It's Nicolas Cage's beautiful mug is on my mug. All right. So this is the example. Let's go ahead and start with part A. First, we are trying to, so again, we're using this method. We're problem solving. What we're trying to find in part A is we are trying to find the density of the metal. And as we talked about last lecture, anytime you're being asked to find a quantity or you're given a quantity that has an equation, it is in your best interest to write out that algebraic expression because it gives you a roadmap, all right, a roadmap towards finding it. Because we know density is equal to mass over volume, we know that if we have our mass and we have our volume, we can find our density. And wouldn't you know it, we're given the mass of the metal is 0.402 grams, and the volume that this sample occupies is 0.908 milliliters. So we have our mass, we have our volume, we can find our density. Density is equal to 0.402 grams over 0.908 milliliters. So now it's time to bust out our calculators. 0.402 divided by 0.908 comes out to be. My calculator is telling me that the density is 0.4427312. The number keeps going, but we don't have to. You'll notice that our numerator has 3 sig figs and our denominator has 3 sig figs, and since we're doing division, you roll with whichever number has fewer. In this case, it's a tie, so we can only have 1, 2, 3 sig figs. This 7 is going to round up. So density is equal to 0.442. It's the correct value. Well, no, it's not the correct value. What did we just say? 7 rounds up, so this is no longer a 2. It should be a 3. All right, that is the correct value with the correct sig figs. And notice for units, oops. In the numerator, we have grams. The denominator, we have milliliters. These do not cancel. So the units for density, for this density, is grams per milliliter, and that will always be the case with density. You'll always have mass in the numerator, volume in the denominator. So this is the answer for part A. All right, now let's go to part B. We are being asked to find the volume, right? Determine the volume in liters. We're being asked to find volume with units of liters. Let's look at what we're given. All right, right off the bat, you could say that, okay, we are given we're given a mass. We're told that the mass, we're asked to determine the volume of a sample that has a mass of 58 kilograms. All right, and that's all that's given there. And so you may be looking at this and go, well, how do we relate mass to volume, right? You might hit, just kind of your gears might grind to a halt. One of the things that you should be aware of, and this is how I format a lot of problems, you'll definitely run into this on exams. This is kind of how I write them. If you're doing a part B, a part C to a problem, and it feels like you don't have enough information to solve it, you should look in your rear view mirror, because most likely what I asked you to find in part A, you'll need to use in part B. All right, these are in sequence for a reason. And what did I ask you to find in part A? I asked you to find density. We know the density of this metal, which relates the mass to the volume. All right, so for given information, I actually didn't give this to you, but you determined it yourself in part A. You know that the density of this metal is 0.443 grams per milliliter. And you also know that the density of a metal is equal to its mass divided by volume. Now, when you look at this, we know our density, we know our mass, we can find our volume if we solve this expression algebraically. So let's go ahead and do a little bit of algebra. We have density is equal to mass over volume. Now we need to get volume isolated on one side of this equation. To do that, the first step is going to be to jailbreak it out of this denominator, right? We don't want to know what 1 over volume is. We just want to know what the volume is. So we're going to multiply both sides of this expression by our denominator so that it cancels. And this gives us the expression volume times density equals mass. Now, we want to find volume by itself, so we're going to divide both sides of this expression by density, and we get the, well, density cancels. Um, and we get the new expression, volume is equal to mass divided by density. And as we already pointed out, we know our mass, we know our density. Now we can find our volume. So let's go ahead and solve the situation. All right, so we have, just rewriting that expression, volume is equal to mass over density. Our mass is 58 kilograms, and our density is 0.443 grams per milliliter. You'll notice that as I'm doing these problems, you'll notice I'm writing my units every step. Not every student does this. I am a strong advocate of doing so, and here's why. If you don't write in your units, you might put 58 over 0.443, hit enter, get a number, move on. And that answer would be incorrect. The answer would be incorrect because look at your units. You have mass units of kilograms in your numerator and grams in your denominator. These do not cancel. All right, these cannot cancel each other. So what we need to do is we need to do a unit conversion before we crunch our numbers. All right, and if you're not writing your units in, you might miss it. The reason why I do that, I write in my units every step, is because if I've forgotten to do a unit conversion, it'll tell me kilograms can't cancel grams. I need to convert. So I'm going to convert 58 kilograms to grams just because that seems easier than converting 0.443 grams per milliliter to kilograms per milliliter. This one seems simpler, so I'm gonna roll this way. I want kilograms in my denominator, grams in my numerator. And again, this unit conversion I will not provide for you because it's one of the metric ones that you just need to know. 1 kilogram is 10 to the third grams because that is the unit multiplier for kilo. Kilograms cancel. And now we have to punch this into our calculators. Your calculator will tell you that 58 times 10 to the third is 58,000. One thing you'll notice is Sig Figs wise, we're fine. We start with 2 Sig Figs. We end with 2 Sig Figs, so we don't need to round. We don't need to add any decimals. And the units here are in grams. Now they are compatible with the mass unit in our density. These will cancel. These cancel each other. So now we're ready to actually find our volume. Let's revisit this. So our volume, at the risk of being redundant, let's add this one more time. Volume is equal to mass divided by density. And our mass in grams is 58,000 grams. Our density is still 0.443 grams per milliliter. Happily, our mass unit cancels. And I'm not going to do 58,000 divided by 0.443 in my head. That's what calculators are for. So 58,000 divided by 0.443 comes out to be a huge number. Comes out to be, oops, I don't want this red. 130,925.5079. All right. Let's look at our Sig Figs. You'll notice that in our numerator, we have 2 Sig Figs. In our denominator, we have 3. You got to doing division, so we got to roll with the fewer number of sig figs. So we can keep 1, 2, 0 rounds down. So our volume is equal to 130,000. That's the correct value with the correct sig figs, right? 2 sig figs. And our units here are milliliters. And that is a problem. You'll notice that we were asked to find the volume in liters. So if you write 130,000 milliliters down, and if you left that as your answer on the exam, remember, it takes 3 things to make a correct answer. You have to have the correct value, the correct units, and the correct sig figs. This answer has the correct value and the correct units, but it does not. It has the correct value and the correct sig figs, but it does not have the correct unit. So we need to do one more unit conversion to get full credit on this problem. All right, so we're going to put milliliters in the denominator, so it cancels. Liters in the numerator. 1 liter. 1 milliliter is 10 to the negative third liters. So now milliliters cancel. When you punch in 130,000 times 10 to the negative third to your calculator, it tells you that your answer is 130. You'll notice that you have 2 sig figs, which we should, but now our volume is in liters. So this is the answer to part B, determine the volume in liters that 58 kilograms of this metal would occupy. All right, so this was kind of like a next level example. This is something that is totally fair game on the exam. You can see something very, very similar to this come test day. All right. So the last thing we have to discuss in this chapter, density was kind of a great kind of pulling together of a lot of different things we've been looking at, rules for sig figs, algebra, unit conversions. The last thing we have to look at in this chapter is temperature. All right, temperature unit conversions. There are 2 temperatures temperature units that are commonly used in science, degree Celsius and degree. So here, well, let's get into this. All right, let's talk about temperature. So, the temperature units that we use, if I told you that it was 65 degrees today, your brain living in the US would assume that we're talking about degrees Fahrenheit. All right, Fahrenheit is the English unit for temperature. All right, Englist. How's that? English. There we go. The metric system's unit for I said unit for Celsius. Unit for Kelvin is degrees Celsius. But there's actually another temperature unit used in science, almost as much as Celsius. They're both kind of present, and so we need to be familiar with both of them. And that is, there's also Kelvin. Notice it's not degrees. So this is you'd say Kelvin. The Kelvin scale is also metric. All right, so we use both of these in the metric system. In the English system, we use Fahrenheit. If you're wondering why are there 2 different units, the reason why is actually will come into play when we look at the gas laws a little bit later this semester. the Kelvin scale is known as an absolute scale. It's an absolute scale, which means that 0 Kelvin is the absolute lowest. It's the absolute lowest temperature. All right, that's why it's called the absolute scale. And this becomes important because as we look at different expressions that have temperature in the denominator of an expression, we all know that bad things happen when you divide by 0. Unless you're in a calculus class, then that's when all the awesome things happen, when you divide by 0. Like the really awesome things happen. But if we're not in calculus, then we just know, our calculator can't handle it. Divide by 0, don't do it. And Celsius, there's 0 degrees Celsius, and then it goes into negative numbers. There's 0 degrees Fahrenheit, it goes into negative numbers. With the Kelvin scale, the lowest possible temperature is 0, so you will never actually hit 0 Kelvin, and you'll never divide by 0. So that's why it's used in some circumstances for the metric system. There are 3 different equations for, there's a handful of equations for converting between different temperature units. You do not have to have these memorized. I will provide the temperature unit conversion equations for you. So these are the unit conversions. So the conversion to find the temperature in degrees Fahrenheit from degrees Celsius is equal to 9/5 degrees C plus 32 to go from degrees Fahrenheit to Celsius. So if you are in Fahrenheit and you want to find Celsius, the equation is just the algebraic rearrangement of the one above it, but it looks like this. You go 5/9 times degrees F minus 32.0. And then finally, the conversion from Kelvin to degrees C is Kelvin is equal to your temperature in degrees Celsius plus 273. All right, and that will convert Celsius to Kelvin. Something that you should know as far as Sig Figs go, this ratio right here is exact, so you don't need to worry about this limiting you to 1 sig fig. But then the numbers that we're adding, all of these, are not exact. So you don't need to worry about that fraction limiting your sig figs, but the numbers that we're adding in all of these equations will limit your sig figs. And again, I will provide these for you on the exam cover sheet. There will be a periodic table and the expressions you need, algebraic expressions, and these will be on there, so you don't have to memorize them. You do, however, need to know how to use them, and so let's do some practice. So let's convert 65 degrees Fahrenheit, which is about our temperature outside. 2 degrees Celsius. All right, so we've got to use the equation that converts Fahrenheit to Celsius. So degrees C is equal to 5/9 times the temperature in degrees Fahrenheit minus 32. All right, so this equals 5/9. Our degrees Fahrenheit are 65 minus 32.0. Sorry, I forgot that up here. 65 minus 32 is 33. You'll notice Sig Figs wise, this is precise to the ones place. So our answer is to be precise to the ones place. And now we multiply this by 5/9. So 33 times 5 divided by 9 comes out to be 18.333 forever. We, however, can only keep 2 Sig Figs and 3 rounds down. So our answer with the correct value is 18. Correct units, Sig Figs is 2. Correct units, here are degrees Celsius. So 65 degrees Fahrenheit, which is I consider to be a pleasant temperature, comes out to be 18 degrees Celsius. Let's do a couple more. All right, convert 25 degrees Celsius to degrees Fahrenheit and Kelvin. All right, so let's convert this to degrees Fahrenheit and to Kelvin. So to convert from Celsius to Fahrenheit, we use the equation degrees Fahrenheit is equal to 9/5 times your degrees Celsius plus 32. So this is 9/5 times 25 plus 32. So 25 times 9 divided by 5 comes out to be 45 plus 32. You'll notice we kept 2 Sig Figs here. And now when we add these two together, we get 77 with Sig Figs. You'll notice our last Sig Fig is in the ones place, and our unit is degree Fahrenheit. So 25 degrees sounds cold to our Fahrenheit ears, but 25 degrees Celsius is actually fairly pleasant when it comes to Fahrenheit. 77 is a nice, comfortable temperature. Now let's convert 25 degrees C to Kelvin. Kelvin is equal to your degrees C plus 273. All right, so Kelvin is going to equal 25 plus 273. When you punch this into your calculator, it comes out to be 298. Sig Figs wise, both 25 and 273 have their last significant digit in the ones place. 298 also has its last significant digit in the ones place, so we do not need to add any decimals. We don't need to round. 298 Kelvin is the correct value with the correct units and the correct number of significant figures. So that's kind of an intro on how to use these equations. They're not too terrible. And again, you don't have to memorize them. They'll be provided for you on the cover of the exam. Now, this brings us to the end of Chapter 2. Um, and now we get to begin chapter 3. All right, so chapter 3 is a study of the periodic table and atomic structure. And we're going to begin with a discussion of atomic structure. All right, and when we're talking about atomic structure, so there are 3 subatomic particles that we will be discussing in this class. So atoms are composed of protons, neutrons, and electrons. All right. For those physics aficionados in the audience, you may be going like, well, what about quarks? What about neutrinos? What about... There's a bunch of other subatomic particles, and there are, but that's a different class. That's particle physics. This is chemistry. So the subatomic particles that we are concerned with as chemists, protons, neutrons, and electrons. The symbol for each, so a proton is symbolized with a lowercase p and a plus sign because it is positively charged. Neutrons are, the neutron symbol for neutron is a lowercase n, and the symbol for an electron is a lowercase e with a minus sign superscripted to the right of the symbol because electrons are negatively charged. All right. So that is what atoms are made of, and there are different configurations of these that lead to different elements, different ions, etc. We'll get into all of that as we move through it. Through the material, one thing I want to touch on before we get too far ahead of ourselves is the periodic table is an array of all the elements that we know. And I want to highlight some of the information available on the periodic table to you really quick. I'm sure you've been exposed. Some of you may have been exposed to this before. Some of you haven't. It'll be a review for some, but I want to just make sure we're all on the same page. So, for example, if you look at, I'm going to highlight everyone's favorite element, silicon. So if we look at an individual cell of the periodic table, there is the elemental symbol, which is front and center. So this is the elemental symbol. All right, and every element on the periodic table has a unique elemental symbol. And some of them are comprised, most of them actually have an elemental symbol that is just one letter. Others have elemental symbols that are 2, like you can see here. Silicon is Si because just S by itself is sulfur. So when a letter is already taken, they will add a second letter to differentiate them. Now I have to make a quick little point. Something that I want you to notice is in the elemental symbol. First, you have if you have 2 letters in an elemental symbol, the first one is a capital. The second one is lowercase. And this is important. All right, first one's capitalized, second one is lowercase. Now, as we move through the course, you're going to see me write elemental symbols. And for example, if I write out iridium, the elemental symbol for iridium is IR. You'll notice that I technically didn't write the lowercase letter for R. This is a capital R. But what's critical here is it is smaller. All right. I'm not going to grade you. You're not going to lose points if you write a capital letter for the second letter in the symbol. You will lose points if it isn't smaller. All right. This also goes if you write a lowercase letter that isn't smaller than the capital letter you wrote next to it. And the reason why you will lose points, if it can be a capital, but it has to be smaller. If it's not smaller, you'll lose points. And here's the reason why. Let's say you were doing a problem that involved cesium. All right, the cesium is an element on the periodic table. And if you look at the elemental symbol for cesium, it's C with a little s. Note, if you don't make that s smaller, this is not cesium. This is carbon and sulfur. All right, that is why it's critical that the letter that comes next must be smaller. I don't care if you use a small capital or a small lowercase, but if you don't make it smaller, you're going to lose points because there are many elements like this whose elemental symbol has a second letter that if it's capitalized or is larger, is a different element entirely. So you gotta make this situation smaller, whatever you're using, capitals or lowercase. All right, so rant over. Be aware, don't make that mistake. There's our elemental symbol. All right, now what else is waiting for us on the periodic table? Floating above the elemental symbol for every element on the periodic table is something known as the atomic number. The atomic number is symbolized with a capital Z. For silicon, Z equals 14. And the atomic number is equal to the protons in the nucleus. Or the number of protons at the core of that atom is given to you on the periodic table by the atomic number. All right, there is, it's worth mentioning that there is also a number underneath. This is called the atomic mass. That is the amount one atom of that element weighs, and the units you'll notice there are no units underneath for any of the atomic masses on the periodic table. That's because they are all in AMU, and they decided to save space instead of having to type AMU after every single one. AMU stands for atomic mass unit. It's a clever name for a clever number. The one last thing, not every periodic table has this, but the periodic table I provide you on the exam will also have the name of the element underneath the atomic mass. So you've got the atomic number up top, the elemental symbol, atomic mass, and then the name. The reason why I include a periodic table that has the names is I do not require you to memorize any elements on the periodic table. That's what Wikipedia is for. I have a stepdaughter who's in 7th grade now, and this past year she was doing middle school physical science, and she did a segment on chemistry, which I was excited for until she told me that she hated it, and which made me really sad. And I asked her why, and she said that she had to memorize like the first 20 elements on the periodic table, and that's when I realized that she was conflagrating her hatred of memorization, which I hate memorization too, with a hatred of chemistry. So it made me sad that there was that confusion was made. It's like, oh yeah, well, memorization does stuff, but chemistry isn't memorization. It's so much more. I mean, I'm a nerd for this stuff, so not everybody's going to love it. But anyways, I will not do to you what my stepdaughter's middle school science did to her. You don't have to memorize any element names. They'll all be provided for you on the exam. All right. So on the periodic table, we have the atomic number, number of protons, the elemental symbol, and the mass, how much each element weighs. One thing you'll notice is that there is no information about electrons or neutrons. All right. And the answer is twofold. First, let's talk about the electrons. So, something you should know is that, so for neutral elements, have no net charge. That doesn't mean they don't have charged particles, because as we can see, every element on the periodic table has protons, which are positively charged. But neutral elements have no net charge. This means that the total positive charge and the total negative charge cancel. In other words, for each proton, there is one electron. All right, so this is true for neutral elements. It's not true for ions, which we'll talk about those later. But what that means is you can look at the periodic table for any element, and because neutral elements have no net charge, for every positive there's a negative to cancel, so the total sum is 0. For every positive 1 there's a negative 1. 1 minus 1 is 0. That means that the atomic number tells you the electrons for a neutral element. So, for example, silicon has 14 protons and 14 electrons. Even though it's technically the number of protons in the nucleus, because we're dealing with a neutral element, the number of negative charges has to equal the number of positive charges. So the answer to the question where the electron's at comes from the atomic number. Neutrons are a different story. So to figure out where the neutrons are, you need additional information provided, and that information comes from something called the mass number. All right, the mass number, which is abbreviated with a capital A, is equal to the sum of the protons in the nucleus plus the number of neutrons in the nucleus. All right? So that is the mass number, and you'll notice the mass number is nowhere on the periodic table. That is because you need well, here actually. So the mass number is not present on the periodic table. You have to be provided that information because the mass number identifies the isotope of an element that you're dealing with. So let's throw down some nomenclature here. So you can have elements. When we talk about elements, all atoms of an element have the same proton count. They have the same number of protons in their nucleus. But they don't have to have the same number of neutrons. This gives rise to something known as isotopes. Isotopes are atoms of the same element. With different neutron counts. All right, so that is an isotope. They're atoms of the same element that have differing neutron counts. All right. Switching from coffee to LaCroix. That's how you know you made it halfway through lecture. All right. So, elements, when you talk about elements, an element is you ID an element with the atomic number you identify an isotope with its mass number. All right, so there are three different ways you can identify an isotope. So we're talking about all right, three different ways to identify an isotope. So this is a little bit of isotopic nomenclature. You can write the elemental symbol and then superscripted to the left. You can have the mass number and subscripted to the left. You have the atomic number. That's one way to identify an isotope. You could also write the elemental symbol followed by a dash and the mass number. That's another way you can identify an isotope. The third way is you can write the element's name with a dash followed by the mass number. These are the three different ways of identifying any isotope. One thing you might notice is you might think, well, the first way seems like the best because this is the only one that gives us the atomic number. And you are correct. It is the only one that gives you the atomic number explicitly. But remember, if you have the elemental symbol or the name of the element, you can find that element on the periodic table. Let's say, for example, you had calcium 8, sorry, not 18. Calcium 38, there we go. The isotope. and you were asked how many protons? How many protons? How many neutrons? How many electrons? Well, you're like, well, I wasn't given the mass number for this thing. How am I supposed to know? You find it on the periodic table, and there you have the atomic number. Sorry, you've been given the mass number. There's the atomic number. So the number of protons for calcium-38 is 20. And because elements are neutral, net neutral, if we have 20 protons, we have 20 electrons. Now, how do we get at the neutrons? We do that through the mass number and the atomic number. Because remember, your mass number, gotta skip this over just a little bit. Your mass number is your protons plus your neutrons. And your atomic number is just your protons. So if you subtract your atomic number from your mass number, A minus Z, protons cancel, A minus Z is equal to just your neutron count. So the number of neutrons here would be 38 minus 20. Calcium-38 has 18 neutrons. All right, so that's how, if you're given an element or the name of an isotope that doesn't explicitly state the atomic number, turn to the periodic table, find the atomic number on the periodic table, and you'll be off to the races. Let's do a few examples. So determine the number of protons, neutrons, and electrons. Oh, that's a little crushed. For each neutral isotope. All right, so we're going to do a few of these. Let's start with sodium-23. All right, so remember, we've been given our mass number here, which the mass number gives you the protons and the electrons because we're dealing with the neutral isotope. So for sodium, we have 11 protons, 11 electrons, and then for our neutrons, we have to subtract our atomic number from our mass number. So this would leave us with 12. So 11 protons, 11 electrons, 12 neutrons. Those are the protons, electrons, and neutrons in a neutral isotope of sodium-23. Let's do another example. Let's, same question, right? Same problems. Let's do it for gold. Gold 197. All right, so first off, we need to find gold. Wouldn't that be nice? Who wouldn't want to find some gold? We have to find gold on the periodic table, and gold is one of the weird ones whose elemental symbol is actually based off of its Latin name. This is another reason why I put the names. It'd be too small to read them on this periodic table, but the periodic table you will be provided will have the name of every element underneath it. So you might take a little hunting, but gold, eventually you'll find it. It's right here on the periodic table. And it has the atomic number of 79. So that means that we have 79 protons and 79 electrons, because again, we're neutral. Now we need to find our neutron count, which we get by subtracting our by subtracting our atomic number from our mass number. So that's an 8, that's a 1, and that's a 1. So our isotope of gold 197 will have 118 neutrons. All right, and that is our answer for gold 197. Let's do one last one. Sophia, great question. So Sophia was asking, how do we know that this element is a neutral isotope? And the answer to that question is the only reason why you know it is because it was stated in the problem. We're asked to determine the protons, neutrons, and electrons for each neutral isotope. So that is how you know, is we've been told. If you weren't told that, you wouldn't necessarily know, and there'd be no way to determine it. So that information has to be provided for you. Another way you can know is if you're dealing with an element, elements by default are neutral. If they're not neutral, then they're ions, and so they have a different categorization. So elements are all neutral by default, and you either have to be told that you're dealing with an element or a neutral isotope in the problem to know that your proton and electron count are the same. Excellent question. All right, let's do one last example. Let's look at the isotope, the neutral isotope, fluorine 19. So we have to find fluorine. First one is right up here. So fluorine has an atomic number of 9. This tells us that we have 9 protons and 9 electrons, because again, neutral isotope. To find our number of neutrons, we need to subtract our atomic number from our mass number. This leaves us with 10. So 10 neutrons in the isotope fluorine 19. All right. Okay. So we're familiar with the concept of isotopes. We're familiar with the concept of elements. Elements have the same proton count, just reiterating. Isotopes are atoms of the same element that have varying neutron counts. All right. Now, there we go. Okay, so there are, for example, 3 naturally occurring isotopes of carbon. There's 3 different isotopes of carbon found in nature. There is the isotope C12, C13, and C14 are the 3 isotopes of carbon you find in nature. If you go out, you take a sample of carbon atoms, you're going to find, you could potentially find all 3 of these. Now, if we look at them, and if I were to ask you how many protons are in carbon 12, you look it up on the periodic table, and you see it has an atomic number of 6, so that means carbon 12 is 6 protons. If I asked you how many protons are in carbon-14, it's going to be exactly the same. Same with carbon-13, because these isotopes all belong to the same element. They all have the same proton count. We're talking neutral elements, they're going to have the same electron count as well. So the only difference here is going to be in the neutron count. Carbon-12 has 6 neutrons, carbon-13 has 7, and carbon-14 has 8 neutrons. Now, if you were to look at the masses of each isotope, they're going to have a different mass because they have a different number of particles in their nucleus. Carbon-12 has an atomic mass of 12.0000 AMU. Carbon-13 has a mass of 13.0034 AMU. It's a little heavier because it has an additional neutron. Carbon-14 is the heaviest of them all because it has the most particles. It has an atomic mass of 14.0032 AMU. All right, now, this is where things get a little interesting. So there are 3 isotopes of carbon, and they have 3 different masses. But when you look it up on the periodic table, right, if you bust out your periodic table and you're like, wait a minute, what is the mass? What is the mass of carbon? The periodic table will tell you, well, first, it gives you 1 mass. And you might be going, okay, well, 1 mass, maybe it's an average, right? Maybe they take an average of these 3 isotopes of carbon found in nature. And let me tell you that if you took an average of 12, 13, and 14, you added up 12 plus 13 plus 14, divide by 3, the average of these 3 numbers is going to come out to be 13. 13 is right in the middle. But if you look at the periodic table, carbon has an atomic mass of 12.01 AMU. Which might leave you going, how the heck is that possible? Right? That's almost identical to the atomic mass of carbon-12. Why is it so close? What about 13 and 14? There's 2 other isotopes and they both weigh heavier. Why is the atomic mass of carbon so low? What's going on here? And the thing is, the mass presented to you, the atomic mass presented on the periodic table, is an average, but it's not a straight average. It's something known as a weighted average. Now, a straight average is what we did. If we add these 3 together, divide by 3, that's a straight average. And the assumption behind a straight average is that the 3 things that you're averaging are present in equal quantities. And for isotopes, they almost never are. All right. If you look at the percent abundance, so of all the carbon in the universe, at least on planet Earth, maybe. No, I can say in the universe, actually. This is based on physics. So of all the carbon out there in the universe, 98.93% of it is carbon-12. Of all the carbon out there, 1.07% is carbon-13, and 1 times 10 to the negative 10th percent is carbon-14. So what a weighted average does is it doesn't just take into account the mass of each carbon, it takes into account the abundance of each carbon. The reason why the periodic table tells you that carbon has an atomic mass of 12.01 is because almost all carbon in the universe is carbon-12. There is a severe minority of carbon atoms is carbon-13, about 1 in every 100, and an almost undetectable amount of carbon out there, carbon atoms, is carbon-14. It's a very, very, very severe minority. So the number, the atomic mass on the periodic table presented to you is a weighted average. It takes into account not just the mass of each isotope, but the percent abundance. And I'm going to show you how to calculate a weighted average right now using these percent abundances. All right, so let's talk about a weighted average. The way you calculate a weighted average is you take the number, right? So like the first mass, you multiply it by its percent abundance over 100, and then you add the next mass, the next number, times its percent over 100 plus ... however many isotopes you have, right? So I'm going to go to the nth because this could be any number of them, times its percent abundance over 100. Just as a refresher, the reason why you put your percent over 100 is you can't multiply a percentage by a number. This is just converting. This converts percent to a decimal. So that's why you're doing that part. So you multiply each mass by its percent abundance over 100, and then you add them all up. All right. So let's calculate. Let's use the isotopic masses and their percent abundances to calculate the atomic mass of carbon. All right. So our first mass is 12.0000 AMU. And we're going to multiply this by its percent abundance, which is 98.93 over 100. We're going to do the same for the isotopic mass of carbon-13, which is 13.0034. We need to multiply this by its percent abundance over 100. And then we're going to do the same for carbon-14. All right, now let's crunch some numbers here. So first, we're going to multiply each isotopic mass by its percent abundance. Then we're going to add these three together. All right, so you multiply 12.0000 by 98.93 over 100, and it comes out to be 11.8716 AMU. Now, when you look at your Sig Figs here, 12.0000 has 6 significant figures, but 98.93 only has 4. So our answer is going to be limited to 4 significant digits. So I'm going to count them off. 1, 2, 3, 4. I'm not going to round right now. You should always wait to round till the end of the problem. So I'm not going to round this, but I'm putting these lines here to remind myself that this is the last sig fig, that 7 is the last significant digit in the number. All right, let's multiply 13.0034 by 1.07 divided by 100. This will come out to be 0.139. Let's see, let me skip this over just a little bit. 1391359 AMU. All right. When we look at sig figs here, our atomic mass has 6 significant digits. However, our percent abundance has 1, 2, 3. So that means our answer can only have 1, 2, 3. Again, I'm not rounding. I'm waiting to round till the end, but I'm putting these lines to remind myself that these are the significant digits of this product. Now let's look at 14.0032 times 1 times 10 to the negative 10th divided by 100. This comes out to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 4, 0, 0, 3, 2, A, M, U. It's a little scrunched there, but we can swing it. Our atomic mass has 6 significant digits. Our percent abundance, however, just has 1. Ooh, that yellow is almost imperceptible. Let's pick a different. So dark blue, 1. So this number has 1 sig fig. Again, I'm waiting to round till the end. Now, we need to add these together. Okay, great question up in the chat. Sophia, why do you not consider the 100 in the sig figs? The reason why is because you got to remember, with significant digits, sig figs only matter, numbers only have significant digits when they are measured. And this 100 is not a measured quantity. This 100 is based on the definition of a percentage. So the definition of a percentage is it's out of 100. Right? That's not measured. That's not a measured quantity. We didn't get a ruler out and measure how many parts are in 100. We define percentage as being out of 100. So these hundreds in the denominator are not measured, and so they do not affect our significant digits. The percentages in the numerator, however, are measured. So those affect our sig figs, but the 100s, that's just part of the definition. All right. Sophia, great question. Great question. All right, so now let's add these up. When we add these 3 together, we get 12.0103900140032. When you look at your last significant digit, because we just did addition, you have to look at the precision of all the numbers you added. And the least precise number right here is our 11.8716 because its last significant digit is in the second decimal place. That means our answer must have its last significant digit in the second decimal place. 0 is a number that rounds down. And so our final answer is 12.01. And our units are AMU, which if you look up the atomic mass of carbon on the periodic table, it comes out to be 12.01. So I don't normally do this. I like to typically keep my exam questions, what's going to be on the exam, kind of close to the chest. But I want to it's, exam 1, it's the first test. I want to give you something to go on. This type of problem this is totally exam 1 caliber. Oh, hang on. All right, so you can expect to have a problem on the first exam where you will be calculating a weighted average and determining the atomic mass for an element on the periodic table. So this is totally exam 1 caliber. You will get a problem like this on the first exam, so this is definitely something you want to practice. All right. So, with that being said, I wanted to so we're gonna shift gears a little bit and kind of dig into the periodic table. Yeah, that looks about good size. So there are certain kind of elements, to make a chemistry pun, of the periodic table that you need to be familiar with. So when we talk about the periodic table, oops. There are certain features and regions that you need to be aware of and familiar with. The first is when we talk about the group on a periodic table. So group equals column. All right. So the group, a periodic group, is equal to a column on the periodic table. So we would say that helium, neon, argon, krypton, xenon, radon, and the original gangster down here are all part of the same group on the periodic table. When we talk about a row on the periodic table, oops, there's some drift there. Ooh. Oh wait, I know. Watch this. You want to see a cool straight line? Boom. How did I do it with the magic of Photoshop? So when we talk about a row on the periodic table, a row is called a period. So you can move across a period. That's all of these elements here are in the same period. If you talk about a group, all the elements in the same group are elements that share a column. There is a thing called periodic law. And when we talk about periodic law, there's a bunch of different ways to describe it. I prefer a kind of boiled down, a simplified one. Periodic law simply states that elements in the same group have similar chemical properties. All right, elements in a group have similar chemical properties. So that's, again, all the columns tend to be a family of reactivity that all behave similarly. There are regions of the periodic table that you need to be familiar with. So the first of which is you need to be able to distinguish metals from nonmetals. So if you look at where are the metals and the nonmetals, this line between boron and aluminum right here. If you start there and kind of zigzag your way down the periodic table, this line divides the metals from the nonmetals, where the metals are to the left and the nonmetals are to the right. That being said, the one additional nonmetal that you can find on the periodic table is here, because hydrogen, hopefully this comes as no shocker, that hydrogen is not a metal. So you're going to have all your nonmetals on this side of the tracks. On the flip side of the tracks, you're going to have your metal heads. So all these ones over here are all metals, and you can see that there are way more metals than nonmetals, including this little floating island down here. These are all metals. So these are our metals. These are our nonmetals. Here and here. And you do need to be able to identify this. I could ask you on an exam, identify your metals, identify your nonmetals, etc. There's a third category of thing. So all the elements that kind of occupy this region, kind of touching that railroad track that divides metals from nonmetals, these elements are known as the metalloids. All right, kind of all those elements touching the division between metal and nonmetal. These are your metalloids. And the way to think of them is they have some metallic properties and some non-metallic properties. So you've got like your nonmetals, who are like your soft boys, your like acoustic kind of indie people over there. Your nonmetals, right? Kind of the hippy dippy stuff. Then you've got your metalheads, right? They're hard. They're hardcore. They like it that way. Your metalloids kind of bridge that gap. They're like the kind of indie punk kids. They like their stuff hard, but they also like it with like a touch of emotion up in there. You know, you got your emos up in there. So the metalloids kind of bridge that gap between two regions of the periodic table that don't have a lot in common. Metalheads and your soft folk pop people usually don't hang, but metalheads can find some commonality with punk kids, and punk kids can also find some commonality with those indie folk dudes, right? So that's the kind of the way to think about it, and this is something that you will be tested on, identifying metals, nonmetals, and metalloids. And this is the breakdown of the periodic table. All right. So this business is exam worthy. This is totally testable. The next breakdowns I'm going to show you, they're not going to be explicitly on the first exam, but I just want to give you a sense of, I'm going to be using these terms in lecture, and so you need to be familiar with them. I'm not going to test you on them. Don't worry about memorizing them, but I want you to be aware of some different kind of divisions of the periodic table. One is, so if you look at the first two groups on the periodic table, and then the last, 6 groups? on the periodic table. So this region, or these two regions, I guess I should say, these two halves of the same whole are known as the main group. These are the main group elements, both here and here. Wedged in between the main group, you will find a group of compounds known as, oops, swung a little further south than I intended. Down in here, you have the transition metals. The reason why the main group elements are clumped together, categorized together, is because main group elements tend to follow the same predictable patterns of reactivity and behavior, bonding structures, etc. We'll get into all of that later this semester. Whereas the transition metals tend to not follow the rules. They tend to break the rules. They're by far the most varied reactivity you can find on the periodic table is found in the transition metal elements. But because they kind of don't follow any of the rules, they're separated and differentiated from the main group elements, which are, again, very predictable. Now, down, if you're wondering about that floating island beneath the periodic table, so these dudes right here, these are not transition metals. They are technically two groups of elements known as the lanthanides and actinides. And they are even less varied than the main group. So with the main group elements, they have predictable reactivity and behavior. But at each group in the main group, every column in the main group has a unique set of reactivity. So the first column will be in the main group behaves differently than the fourth column. The lanthanides and actinides almost all behave the same in both periods. So they're kind of just clumped together. We're going to talk about them the least. That's not to say that they're boring. There is some very interesting lanthanide and actinide chemistry out there, but it tends to be very, what's the word I'm looking for? Not esoteric. It just tends to be very niche. It's this one specific niche, and if you burrow into it, you can find some very interesting stuff. But from the broad global perspective, they're all kind of the same. And again, this is an intro class, so we're not going to get into that niche stuff. If that interests you, there's some amazing stuff going on in different labs across the U.S. One particularly at UC Irvine, there's a really cool professor who does lanthanide and actinide stuff. But again, you kind of have to go full metal chemist nerd if you want to see the differences between these elements. From the bird's eye perspective that we're taking this semester, we're going to treat them all as identical. Though they're not. They're each their own little snowflake. But in this class, it's just a clump of white stuff. All right. So those are the groups. You've got the main group, transition metals, lanthanides and actinides. The last way I'm going to chop up the periodic table, and again, I want to introduce it here. This will come into play a lot more I almost said next year. I'm sure it will, because I'm going to be teaching the same class. Later this semester, it's going to come into play. This won't be on the this exam, but you will be tested on it later, and I want to introduce it, is we can divide the periodic table into blocks. So the first block is the first two groups on the periodic table form the first block. In addition to helium is also part of this block, and it is known as the S block. All right. The next block on the periodic table I'm going to highlight is the rest of the main group. This is the P block right here. All of our transition metals fall into what is known as the D block. And finally, our lanthanides and actinides have their own block. And this is the F block. Again, this will come into play when we get to electron configurations. So we're going to be doing a lot with these blocks, but I wanted to introduce them here since we're talking about how we chop up, how we divide the periodic table. Which will actually be coming into play by the time this chapter is done. I was like, oh, it'll be later this semester. I forget. So with Chem 400 deals with the blocks of the periodic table almost at the end of the class. But Chem 305, actually, we're going to be dealing with it by the end of this chapter. All right, so that's an intro to the periodic table. It is going to become our best friend, possibly our greatest enemy, over the course of this semester. We're going to continue now with a continue our discussion of atomic structure. So, we've been talking about atomic structure pretty much all class, but up to this point in time, we've talked about subatomic particles. Excuse me. But up to this moment in time, we've more or less treated atoms as just clumps of smaller little beads, right? Protons, neutrons, and electrons. But we haven't talked about how they are arranged. Now, when I say the word atom, probably the first thing that comes to mind is the International Atomic Energy Agency. I think that's what it's called. That one, it's got the ball in the middle with the 3 loops around it. Probably when I say the word atom, the first thing that comes to mind is, you've got a proton in the middle, and then you have an electron orbiting, right? Kind of like a planet orbits the sun. And as far as basic instinct is concerned, as far as the first thing that comes into your head, this is not a bad model of the atom. One thing that probably isn't in your head is the following. So this is probably what your first thing, but I'm going to add a level of detail to it. And I apologize for my lack of circles. These might be the worst circles you've seen since, since kindergarten. So just pretend they're concentric circles. Um, so you've got the nucleus. Right in here. So this is the nucleus. Which houses any protons and neutrons. And then you have the electrons orbiting the nucleus. Now, the one detail that I'm adding, you're like, what are these different circles? These are orbits. So the first one I'm labeling as n equals 1, followed by n equals 2, followed by n equals 3. These are what are known as electron orbits. So these are electron orbits. And what's weird is, so like we think about the electron, orbiting the nucleus, it's spinning, it's spinning, it's spinning. But what's weird is that the electron is not free to be anywhere in space. It can occupy the first orbit this far from the nucleus, or it can jump up to the second orbit and orbit this far from the nucleus, or it can jump up to the third orbit this far from the nucleus. There's more, there's n equals 4, etc. But it cannot be anywhere in between. All right? Little bit of vocabulary here. So these electron orbits, or with respect to these electron orbits, the energy level, right, n equals 1, equals 2, equals 3, is called the electron shell. All right. So you can hear me refer to the first shell, second shell, third shell. That's what I'm referring to. And the larger the shell, the higher the energy. All right, the larger the shell, the higher the energy. So the further and further away you move from the nucleus, the higher in energy that electron will have to be to occupy that shell. So you can also notice n equals 1 is closer to the nucleus, and it's the lowest in energy. N equals 2, you move farther from the nucleus, and it's higher in energy. N equals 3, 4, etc. So the last thing that I want to point out is the larger the shell, the farther the electron is from the nucleus. All right, so with increased shell comes increased energy and increased distance from the nucleus. Now, the reason why this is think about it. Electrons are negatively charged, protons are positively charged, and those opposite charges attract. They want to get as close to each other as possible. So if you're going to move your electron further from the nucleus, you have to pull them apart. They're a force that want to be close. You're forcing them apart. That takes energy to pull them apart. All right? Now, there are two types of electronic motion around the nucleus. You can have an electron go from a low energy shell to a high energy shell. So if you transition, for example, from n equals 1 to n equals 3. All right, here the electron gains energy to transition from a lower energy shell to a higher energy shell, again, because the electron wants to be as close to the nucleus as possible, and it's being forced apart. You're pulling it apart with energy when you transition from a low energy shell to a high energy shell. Energy is gained. When, flip side of this coin, if you start at a high energy shell and you transition to a low energy shell, here, oops, sorry, I wanted that to be black. Here, the electron releases energy. And the way to think about this is, so we've pulled this electron far apart from the nucleus and we're holding it here with energy. If we let it go, they're going to smack back together, right? It's like releasing a rubber band. It snaps. That energy is released as the electron jumps from being far away, which it doesn't want to be, to being close, where it likes to be, in that lower energy configuration. All right, so these, both the gain of energy as you move from a low shell to a high shell, and the release of energy as you move from a high shell to a low shell, these are called electronic transitions. All right, and so you can gain energy, that's one transition. You can release energy, that's another transition. And the electrons are constantly doing this. As they absorb energy, they hop out to higher energy shells farther from the nucleus. Then they relax, releasing that energy, jumping down to a lower energy shell. It's constantly happening all around us. All right, now the Bohr model adds this level of detail that probably doesn't exist in our basic intuition, right? We're, like I said, we're used to thinking of the electron orbiting the nucleus, but we don't really look at, or at least for most of us, it probably doesn't come to mind that there are these shells, these orbits that the electrons are stuck in, that it can be in one or the other, but nowhere in between. And this is called, by the way, this is all from the Bohr model of the atom, added that detail of the shells, which is good, but it's not actually the current model of the atom. It's not our current understanding of atomic structure isn't the Bohr model. The Bohr model added this concept of shells, which does exist in our current understanding of the model, but of the atom. But our current understanding of atomic structure is one known as the quantum mechanical model. And in the quantum mechanical model, one of the biggest differences is instead of 2D circular orbits, electrons move through three-dimensional orbitals. So that idea that you've got your nucleus and that your electron is spinning in a circle around it is no longer our current understanding of atomic structure. Rather than spinning in a circle, it's actually a three-dimensional shape that the electron is buzzing around and almost moving so fast it creates this blur so that it looks like this shape. That is our current understanding of atomic structure. Now, this idea of orbitals is clutch because there are actually different types of orbitals. There's different types of shapes. One that you probably would imagine would be the s orbital, which is a sphere. All right, so this is an S-type orbital. And it's like that idea of like, okay, it's spinning in a circle, we'll now make that circle a sphere. That's where the electron is moving in three-dimensional space, all right? And there is one s orbital in every shell. But that's not the only type of orbital there is. There's also, there's also a p-type orbital. These are three-dimensional, just like the s-type orbitals are. Where one half is shaded, one half is not, but it's three-dimensional all the way around. This is a p-type orbital, and there are three p-type orbitals on each shell where a p-type orbital exists. I'll get to that in a little bit. There is a d-type orbital, which is kind of, if you took two p-type orbitals and smashed them together to make an S, you would get a d-type orbital. Again, all of these are three-dimensional. They're kind of like balloon animals. And half of them are shaded. So this is a d-type orbital. And on each shell with d orbitals, there are 5 of them. Finally, there is the f-type orbital. And there are 7 f-type orbitals on each shell with f orbitals. And their shape is too gnarly to draw. You can Google it if you want to see what the f orbitals look like. I am not capable of drawing them. I'm not even going to try. The good news is I will never ask you to draw an f-type orbital because I can't. So that's good. Why am I drawing any of these in the first place? Here's the reason. The complexity of the orbital shape corresponds to the energy it takes for the electron to occupy that orbital. So the s orbital is the lowest energy orbital in existence. The f orbital is the highest energy orbital in existence. And drawing their shapes, being familiar with their shapes, I feel like illustrates this well. The S has a simplest shape. It's just a sphere. It is the lowest energy orbital. The f orbitals are too gnarly to draw. They're the highest energy orbital. P is higher than S. D is higher than P. F is higher than D in energy. All right. Now, I just want to let you know that I could ask you to draw these. On a test. Just something to be aware of. That might pop up. I'm not promising it, but it could totally happen. You do need to be able to identify an s orbital from a p orbital from a d orbital. All right. Now, one thing to mention before we move on is, so these designations, s orbital, p orbital, d orbital, f orbital, these are all called subshells. So the shell is the energy level, right? N equals 1, first shell. N equals 2, second shell. N equals 3, third shell. These are all subshells. So you could, for example, have a s orbital on the first shell. So the shell would be 1, subshell would be S. On the third energy level, for example, if you had a d orbital, that would be shell is 3, subshell is d. So a 3d orbital would tell you the shell and the subshell simultaneously. All right. Now, each shell, each energy level has different numbers of subshells available to it. So if we make a little graph with shell energy on the y-axis, for the first shell, there is only the s subshell. There is one s orbital subshell on the first energy level, in the first shell. In the second shell, you not only are gaining an energy level with your shell, you're also gaining an available subshell. On the second shell, you have the s subshell, and there are 3 p orbitals comprising the p subshell. So on the second level, you gain an energy level, you gain a shell. The same holds true with the third. The third shell has the S, P, and D subshells available. The fourth energy level, fourth shell, has S, P, D, and F subshells available. And every shell beyond the fourth, so if we write in the fifth, has all 4 available. Theoretically there's a G subshell, but no element known actually has any electrons occupying a G subshell. So every energy shell beyond the fourth just has these same 4 subshells available. So you start gaining one as you move from 1 to 4, and then 4 and up, 5, 6 are all exactly the same as 4. All right. Okay, so we have come up to right up to the edge of something known as electron configurations. That is the next thing we are going to cover here. So we're coming up to a discussion of electron configurations, and orbital diagrams. All right, that is where we are headed next. We've got 10 minutes left in class, and I don't want to dive into this subject right at this moment. I want to actually save this for next lecture. So we're going to stop here with lecture. I'm going to put a pin here. We will resume next lecture with a discussion of electron configurations and orbital diagrams. The one thing, so the thing that I want to mention in closing is, unless you hear from me, next class is in person. So we are all going to have to get out of bed much earlier and be there 8:15 to 10:20. We will be going, unless you hear differently from me. But there hasn't been any announcement that's gone out. So the assumption is, again, if it changes, I will tell you. And I'll post it to Canvas, but our next class will be in person. So if you are waking up whenever you do and turning on YouTube to go, okay, I'm going to watch lecture now, nothing will be there. You can, of course, if you miss class, use the backlog of lectures from that I recorded in the summer of 2020 to catch up. But but you'll want to be in lecture because that will have all the pertinent class information, and it'll be the actual pace that we're keeping this semester, so you'll know what'll be on the exam based on how fast we're moving through the material now. All right, so I'm going to go ahead and call it there. Thank you, everybody, for joining. Sophia, you asked some great questions today. I can't wait to actually share a classroom with you and meet you all in person. So knock on wood. There we go. Knock on wood. It'll happen on Monday. Have an easy. Take it easy. Have a good weekend, and I will catch you